Hello and welcome. Today, we're exploring an often overlooked resource that holds immense potential: agricultural waste. Instead of just being discarded, this waste can be transformed into sustainable biofuels and valuable biochemicals. This process, known as valorization, is vital for cutting our dependence on fossil fuels, reducing greenhouse gas emissions, and managing waste more effectively. We'll specifically focus on biochemical conversion, a fascinating route where microorganisms and enzymes become tiny factories. So, what's in this agricultural waste? Things like crop residues, straws, stalks, and leaves are rich in lignocellulosic biomass. This biomass is primarily made up of cellulose, hemicellulose, and lignin. Through biochemical processes, the cellulose and hemicellulose are hydrolyzed, or broken down, into fermentable sugars like glucose and xylose. These sugars are the essential starting point for creating a variety of biofuels. Let's look at the key conversion methods. First up is enzymatic hydrolysis. This involves using specific enzymes, such as cellulases and xylanases, to meticulously snip the long chains of cellulose and hemicellulose into simple sugars. A lot of research is dedicated to improving enzyme efficiency and cutting their cost, which is crucial for making biofuel production economically viable. One promising technique involves immobilizing these enzymes on nanoparticles, making them more stable and reusable. Once we have those simple sugars, microbial fermentation takes over. Various microorganisms, including bacteria, yeast, and fungi, ferment these sugars into different types of biofuels. For example, yeast is commonly used to ferment sugars into bioethanol, a well-known biofuel that can be blended with gasoline. Certain bacteria can convert sugars into biobutanol, which packs more energy than ethanol and can be a drop-in replacement in existing fuel systems. Then there's biogas, mainly methane, produced through anaerobic digestion, where microbes break down organic material without oxygen. Biogas can be used for heating, generating electricity, or upgraded to biomethane for vehicles. Europe's biomethane production has seen a significant surge recently. Some microorganisms can even produce biohydrogen. However, lignocellulosic biomass is naturally stubborn and resistant to breakdown. So, a pretreatment step is almost always needed before biochemical conversion. Pretreatment aims to disrupt the complex structure of the biomass, making the cellulose and hemicellulose more accessible to the enzymes. Methods range from physical approaches like milling and grinding, to chemical methods using acids or alkalis. Dilute acid pretreatment is common for maximizing sugar yields. There are also physiochemical methods like steam explosion, and biological methods using lignin-degrading microbes, which are eco-friendly but can be slower. The field is buzzing with advancements. Nanobiotechnology, using nanomaterials, is helping create more efficient and stable enzyme systems and even aiding in pretreatment. Co-culturing techniques, where multiple types of microorganisms work in tandem, can lead to more efficient conversion and a broader range of products. The concept of integrated biorefineries is also gaining momentum. This means using every component of the agricultural waste to produce not just biofuels, but also biochemicals like phenols and organic acids, and even biopolymers, boosting overall sustainability. We also see exciting developments like microbial fuel cells, which use electrogenic bacteria to turn chemical energy in waste directly into electricity. Despite this progress, challenges remain. Managing the logistics of bulky agricultural waste, from collection to storage, can be costly. The composition of waste also varies, impacting conversion. The expense of pretreatment and enzymes is still a significant hurdle. We also need to improve conversion efficiency and product yields. For instance, butanol production needs a boost. Scaling up from lab research to commercial production is another big step. And, critically, we need thorough sustainability assessments to ensure these green solutions are truly beneficial in the long run. Looking forward, research will continue to focus on developing cheaper, more potent pretreatment methods, engineering more resilient and productive microbial strains, optimizing enzyme combinations, and designing smarter integrated biorefineries. The ultimate aim is to make the biochemical conversion of agricultural waste a truly competitive and sustainable pathway for producing sugars and biofuels, contributing significantly to a circular bioeconomy and a much-needed greener energy future. Thanks for listening.